Thank you. Yeah, thank you, Brice, for inviting me, giving the opportunity to talk to you about my further last postdoc project in Berlin. So in brief, we needed to investigate the brain activity of higher neurons in the honeybee while the bee is navigating. And the smallest brain activity amplifier is still many times more heavy than the bee. So we cannot load the bee with an amplifier. We need to carry a whole system with the bee. But it seems that virtual realities for insects are kind of tricky. So we thought to go out in the real world and find a compromise, and having a flying quadcopter moving passively a bee on a stick, so she can have the experience of the real world. But we have some payload capabilities where we have the attached amplifier and we can record the brain activity. So the honeybee is an interesting model organism for these kind of questions, because it has a very rich behavior. It's an eusocial insect, so it's really social like we are. It has overlapping generations. It has shared brood care and a division of labor. When they waggle, that's the shaking motion you see several animals do. They are communicating distance and direction of locations, either locations for a different height they could have, or for a food source. So not every bee independently, like bumblebees and wasps and other animals, need to figure out where good food is, and then they fly privately back and forth. They share the best trees, and then they can be much more efficient in gathering food. And for example, why we want to go deeper into the navigational skills and the information pickup while navigating through the air, for example, the novel shortcuts. So an animal could know a tree, and then also because the tree is more and more empty, is less and less successful, she picks up a waggle dance for a different tree that may be interesting, and then she may fly to the first food source, doesn't find anything, and instead of flying back home like a dumb robot or just an insect, she would immediately figure out a way to get from the one food source without going home to the other food source. So the novel shortcut, it's called. And it has some, and from a laboratory perspective, it's a very thankful animal to have, because you have a wooden box outside. Some have them on their roofs, so you don't even need a garden. There's one person taking care of the hive for maybe 1 hour per week, and then it's fine, and they give you honey, which is always good. And they are microscopic, so they're around a centimeter, they're around 1/10 of a gram. They fly as fast as you cycle. They go up to 20 meters maybe. They live a few weeks. They transport half their body size, and so all of the things they do are within the dimensions that are particularly easy to access with sensors and with cameras and with our human perception and eyes and all kind of things. So it's not like chasing atoms or the universe. It's right there in the middle. And for better or worse, there is so far no paperwork attached. You can do fast prototyping with the animals as well. There's not a long ethical debate about testing an amplifier with insect, which is nice, as you will see later. And the animal can be conditioned very quickly and easily to visual cues and olfactory cues. So my PI once went to a television show and had a harness bee. He puffed on an order once, gave some sucrose solution, and after the break for the advertisement, when they came back, he gave a puff of this solution, and the animal extended the very long, very visible proboscis to show it expect a sucrose solution. So the animal can very quickly and robustly train, and the animal can learn symmetry, asymmetry, and rules and points at the day, so they can tell you what time it is down to 15 minutes precision. And I think without a clock, we wouldn't be any more precise than they are. So it's a fantastic animal, and you can always push the ecological and economical importance of the very heavily human rolled out pollinator. So as I said, we can do lots within navigation, or we are particularly interested in navigation for the aforementioned reasons. And ways to approach the behavior is, for example, to put stickers on the bee. They tolerate that quite well, and then you can release them and look at different points where they may re-enter either a food source or a hive or a trap when they arrive there and how much time that takes. And you can then do some statistics, how directly they flew there. And over time, they had more interesting approaches of using transponders they put on the bee. We would also, they say, handle that reasonably well, and then fly around, and we have the track every second or so in 2-dimensional across several square kilometers, and then we can see what strategies they use to go to certain places, how directly they go there, and I think most interestingly, what search strategies they use once they think they are somewhere, but they can't really find a point of interest. And to investigate then the brain activity of bees while they navigate, so far, we are actually quite successful in the Drosophila concerning orientation. So where am I? Not necessarily where do I want to go, as how far am I from something and so on. They use virtual realities and floating balls where the animal would mostly walk. The flying virtual reality, as far as I know, and my lab has tried several attempts, is not successful yet. And there are reasons to believe that the flying animal is in a different state in its mind, so to say, when it's walking versus when it's flying. So it may be worth investigating the brain activity while the animal is actually flying or in a flying mood and not in a walking scenario. And brain area of interest. So here you can see a depiction of the brain and the head. So here would be the antenna. Here's the back of the head. Behind the yellow visual areas, there are the eyes. And then further central, we have the red mushroom body that I will focus on. And they seem to store the learned information, maybe snapshots of how they get to certain places, connections between chemical odorants and context of visual cues in relation to certain negative or positive reinforcements. And we're quite certain that they are in there, but we don't really now know how the network is saving and or communicating these kind of information. So we have spike activity from cells that output, so they're supposed to inform the rest of the system that something's really good or something's rather to avoid. And we cannot really tie the spike activity changes or pattern to any of these relations. And that's kind of frustrating. So I thought also that it would help to use something as natural, so ethologically relevant to the animal as going to a feeder. So the idea at some point will be that we have a bee that's trained from the hive to fly to a feeder. We will have it on the copter fly to the feeder at the right speed and time. So it should recall all the information right before they should get to the food. That's like the thing they do for their social environment. And then we overshoot the goal, and they should be so frustrated and confused while we overshoot it. That was like the strongest, meaningful stimulation in the real world context we thought should give the animal a very arousal thing. And that should help us tie the spike activity to the outside stimulation. And this brain activity is particularly interesting because it does multimodal integration. It takes pretty much all the incoming information, evaluates them for known or unknown and novel and strongness and so on. So you have the visual cues, the UV and blue and green color that they see, the strongness of these photons as well as polarization. They have the inertia via the hair and most likely the antenna and air movements, order plumes, how their quality and quantity is changing within the air they're flying through. And possibly electrostatic fields, as well as stimulations we don't know yet may be relevant. So the whole coincidence detection and like some days it's all of this coherent doesn't make sense. Here should be fine because we will use the fully synchronized and high resolution reality and not a flickering screen, because we can barely make reasonable VR for people and we can most likely not do it for a little furry alien. And that's why we went for this area with this question. Open hardware, it was kind of a given, even without the name, in Honeybee neuroethology, so to say. We are a small amount of labs that all work closely together, besides a small other island that's entirely shut off. But okay, so we work all together and exchange ideas and protocols and peoples and trainings. Anyway, everyone is doing the same thing. and everyone is pointing to the same source anyway. Nobody talked ever about any licenses or so. They all share it anyway. And we have rather little money because it's kind of a hippie community, and it's not Drosophila or rodents and Parkinson. It's for the sake of knowing how navigation works. And there are no Y mazes or Skinner boxes for honeybees. There's apiary equipment, and that's it. But it's also, for me, particularly interesting because it's super fast. You can build a prototype in a few days, maybe a week, test it on the animals, see the outcome, and then do another revision, and then start the actual work over the winter, let's say, and then do some interesting experiments. And coming back to the mesoscopic size and behavioral scale of the animal, the consumer electronics are really thankfully at a similar scale. So all the sensors look at the kind of temperature that's relevant, magnetic field and the distances and the speeds and accelerations and all these kind of things. And we could find, for whatever question we ever had, the sensor that would fit right in there and maybe even oversample in a decent proportion. So here you can see, anyway, here you can see a bee attached to the copter. Just in the pre-experiment, we wanted to see if we have the animal and force it to fly through the air, if the animal would be in a navigational state. And we thought it would be in a navigational state if it would beat its wings and not just flat there in horror. I don't have the control video where they really try to avoid everything. And here you can see that the animal is nicely flapping its wings and making its legs straight, so it seems to be happy. We counted the amount of time the animal would flap its wings continuously. You can see that it is quite long and significantly longer to the two controls that were either no flight or hovering, in which we had the copter just sitting on the ground and the leaf below the animal that the animal would grab, it would rip away, and then they have the reflex, the palsy reflex of flying, and that would just stop after 4 or 5 seconds, as you can see there for most animals. And even if we would hover at like breast height and rip away a leaf, then the animal would fly for only a short amount of time. The optic flow, the forward movement, the wind movement seems to be relevant for the animal to further engage in flying activity. And we think that's a decent pointer towards the behavior where the animal will pick up all these cues to have a further information about how it is moving in a navigational kind of way. We then took some bees that learned to go from a hive to an artificial feeder back and forth and bring food home. We picked them from the feeder where they would be motivated to go back home. And we carried them in a black box for the control group in a black box to a release site, and then released them and counted the time it takes them to fly back. And we did the same thing with other bees where we caught them and transported them over to the release site where they were attached on the copter. So they could pick up all the visual and other information going from the feeder to the release site. So they had this positional change, how it occurred, what compass rotation occurred continuously. And those animals you could see significantly, mind on the logarithmic scale, please, they were significantly faster in flying back. So they may have helped by picking up the information flying back. So now when you think about electrophysiology, you have an electrode in the head of the bee, in the brain actually, and that electrode is attached to a preamplifier and then to an amplifier. That's, for example, here there's the screen box that is a filter to get rid of the AC hum, so the 50 hertz noise you have from the plugs, and then it's digitized and put into a computer. And that's heavy mostly and big. So that would be very difficult to attach to a drone that would not break the bank. So I found a publication of a very small, lightweight, but very well-performing amplifier that we asked the electric engineer take 2 channels and just put up the PCB with some basic power supply and ABC. And informatics student was kind enough to help me get the data of the ABC onto a Raspberry Pi where it would be saved on an SD card. So all of that was small and cheap, and we could just put it on the copter you saw earlier. It would run on a 12-volt battery, I think, and we could even use the same battery as the copter. because the noise wasn't too bad, and the DC converter just cut off all the ripples, and then it was fine. Here you can see the main board. Here were the electrodes attached for these two monopolar channels. And then this was broken off and put very close to the bead so that the electrodes were as short as possible. I think in the end, they were maybe 2 centimeters long. They were twisted together, so the noise pickup would be identical. And this pair was then set into the brain of the bead. And here the already impedance transferred, so the stabilized signal was then sent back to the main board in the center, where it was further amplified by roughly 10,000 fold and actively filtered on 2 bands, and then here put into 2 separate ADCs. So they were not multiplex, so 1, 2, 1, 2 super fast, but both of them triggered at exactly the same time, and that was very important. They will be triggered simultaneously, so any noise they may pick up from a super high frequency movement of the robots and even higher current bursts from the motor controller. This could then be subtracted later on digitally to recover the brain activity. And the bandpass was quite nice between 100 Hertz and 20 kilohertz and 16-bit depth, so we could have a large window where there was some movement of the baseline, and we still would have nice signals. There was a little bit of power draw, but the machine was drawing hundreds of amps, so a little 100 milliamps were not relevant. Interestingly, the system is rather cheap. It costs around 100 euro per channel because of the very expensive ground chips. But that's still like several orders of magnitude cheaper than any commercial solution. So here you can see now the input channel. For testing, we sweep through frequencies that are relevant for us. Here you see output, and you can see that the amplitude and, more importantly, the timing, so the pace of the maximum, supposed to be synchronous, but it is not. It is frequency dependent, and the amplitude is, so the size of the signal is also frequency dependent. In the frequency, that is relevant. So that was very bad. It turned out that there was an error in the initial publication, and because the way publications work, not so open and kind of static in a terrible way. After a while, looking around, the author of the initial AMP told me that they found the error themselves, but they never published it because now they have a company building AMPs, and it would be kind of dicey to show that there was an error. So they rather kept it by themselves. They congratulated me that I was the first one to build that system anyway, after 10 years of having it published. We put the correction into the PCB design that we published with all of this. We didn't make a thing, it's, but yeah, that was interesting, because it was also very difficult to get the engineers and the informatics to believe the biologists that there's something wrong with the signal. So then we, as I told you, we had these that were trained in the institute to go to a PDA. The institute is around here across the street. It's in the middle of Berlin, so we could not fly over the street. Also here was the embassy of Iran, and around here was the embassy of the US. So we stayed exactly on top of the government area. We had a written allowance, and it was fine. So we started roughly here as protected, the closest we could get from the height. We would fly as the bee would towards the feeder that was standing there for weeks, and the animals, it was late fall, so there was nothing but this. They could have 50% suture solution, which was pretty much like heroin in this season, or they could have like some marmalade that someone dropped, or some McDonald's soda. So this was fantastic, and there were super many animals, and we counted them, and we used animals that were already flying there for the last 3 days around 50 times. So extremely motivated animals. Cut open their head, attach them to the boom, have good brain activity, get them into my car, carefully driving over to this place, hovering up, and then flying towards the feeder. So everything is as she would do it, with the big difference, she is forced to fly there, because I tell my pilot to let her experience this. And then we fly here, and we don't go down. We fly over the feeder, around the feeder, to approach the feeder again, so have as many towards away of the feeder situations as possible. And this tangle, the orientation, the background, the landmines on the ground, the compass, these kind of things. So approaching this place from different directions. And then doing that several times, flying back, returning and repeat. And after around 5-6 rounds, 20 minutes, the battery would be drained, we would land, change the battery, look for the signal if it's still fine, and repeat until the owner of the building said they're closing and we had to leave. Because we tried that around 500 times over 3 years. We got to the point where we drove over there around 50 times. And when we started the experiments, there were around 5 to 6 animals that still had signals. So it was really a low success rate. So once we had an animal that would work, we would repeat until we were forced out. You can do the brain activity while it was on the ground between battery changes, and I was checking the quality. You can see these are many spikes in the background. There's no hum, no noise, no tickling. It's the unfiltered analog signal, so to say, from the spike activity, and the signal to noise is fantastic. While it's standing, it's the same as you would get from a laboratory amplifier, which I confirmed in the lab by having it plugged into either a commercial unit or my unit, and it was decently the same. Then, so the raw signal from these two monopolar channels was of course awful because of the strong signals from the motors, but we could then subtract them. We did that later digitally because the proportion between the two channels changed over time, because they were highly dependent on the entry point between the electrode surface and the wet tissue that would dry a little. There would be little sheets and movements and swelling that would really change the amount of ions that could flip in and out between the electrode and the brain material. So we had both of them and did later kind of a super slow rolling average subtraction that then would take care of the slightly changing noise. Here you can then see in B how that looks like after subtraction. You can see the nice spikes popping out. Then blowing up the time, you would see the spike pattern. We could make the average shapes, sort them out. And in the interspike interval, we would look how long it takes from each spike to the next spike, because they cannot be infinitely close to each other. Biologically, they are restricted to not spike more than every 4 milliseconds or so, because the cell needs some time to reflect on itself and then do it again. And all of these things are fine. So the quality of the neuronal activity was quite high. And here you can see the time of starting in the corner, climb towards the wall, over the wall, around, and back for the first 5, one of informatics starting with 0, for the first 5 rounds. And then we had that for all of the repetitions for that 1B, for several Bs. But you need to keep in mind that when we blindly poke a super thin wire into the brain of a bee, we may end up at slightly different points, because the tiny volume has still around 960,000 neurons. So the likelihood of getting different cells is kind of high. And our yield was 3 Bs. So we don't really want to pool the 3 Bs here. But now the next obvious analysis would, of course, be use the trajectory of the flight. So at any given time, the copter was somewhere, and we had the spike activity as for color plotted on it. And what you can see here for the first 3 rounds, that mostly the activity was higher in the corner when it was turned around. So of course, the optic flow was much higher in the turning situation, when you can see the rather aggressive curves versus the long stretches. Where we were flying slightly higher than the bees would normally do for security reasons, because there were some people working different experiments that were independent of us, and we don't want to throw a 6-kilogram drone into their heads. And we had instances with other drones years earlier where there were no people, so it can happen that these things fall out of the sky, even if the manufacturer says no. But good. So we were a bit too high, a bit too slow, but rather close to what should be done by the bees. And here you can see that what is really missing is that something is different between here and here, as well as here and here, and again and again. And that really didn't happen. And in whatever way we looked at it, we could not find any difference, or we could not point the brain activity to the feeder in a meaningful way. All we could find was the angular speed was extremely correlated with the spike activity. So here in a control or in different experiments we did earlier, and then the experiment I showed you, whenever there's a curve, of course, there's a strong angular speed, versus pretty much nothing. And whenever that occurs, you can see that the spike rate, so the amount of action potentials per second, goes up as well. So whenever the thing is turning around, the spike rate is quite high as well. And we don't really expect the brain area that is concerned with memory. I mean, attention and expectation, fine. So if you are the bystander in a helicopter and the guy does this and this occasionally, that would do things with our brain as well. However, that's not related to the feeder as we would have had hoped. So that was kind of a bummer, and the number 3Ds as well. So overall, we found that only the turning behavior was related to the brain activity. We think this approach may be useful to have, once there is an interesting navigational finding from the lab, we could repeat the experiment out in the field. Even though the yield would be low, it could really, under these natural conditions, confirm the theories, because maybe in the lab, with the virtual reality, animal may get hooked to some artificial things. But I also want to point out that the amplifier independently is a battery-driven, extremely cheap, small, highly accurate, versatile electrophysiology amplifier that is doing what it's supposed to. So that's kind of a win. So I want to thank my former Professor Metzer, and Helmut and Alexandra for standing in the sun in late fall and poking away hornets and feeding the bees, and also Julian for writing the code to have all the digital ends need, because Wight Stiftung for the money. And of course, these different communities helped me out tremendously to get this done. And if you want any further information, the copter project and its repo is at the first QR, my GitHub, the Gathering of Open Hardware Science. It's a group of people similar to this one that wants to make open hardware ubiquitous in science. There are around 400, 500 people, extremely active across the globe. My YouTube, Twitch, as I stream experiments live occasionally, and my blog that wasn't updated in a decade or so. Thank you. If you have any questions,